Thermal dispersion mass flow meters for low-velocity, low-pressure gas applications. Thermal dispersion thermometers offer a simple, reliable solution for direct mass flow measurement of clean, dry gases at low to moderate flow rates. Using a heated sensor and a temperature reference, these devices infer mass flow based on the rate of heat carried away by the moving gas. They are particularly effective where pressure and temperature vary, but gas composition remains relatively constant, eliminating the need for additional compensation instrumentation. Their no moving parts design, low pressure drop, and insertion style availability make them ideal for ventilation air, nitrogen purging, combustion air, and flue gas measurement. Purge gas and tracer flow verification analyzer shelters. Flare monitoring, and leak detection and submetering of utilities. Mass flow direct from sensor, no pressure or temperature compensation required. Thermal dispersion meters calculate mass flow directly without relying on inferred calculations or downstream compensation. This makes them particularly useful where density varies significantly, e.g. outdoor air, off-gas. Space or cost prohibits separate pressure and temperature instruments. Simple, low-maintenance measurement is required without sacrificing reliability. Service limitations and suitability screening. These meters work best with clean, single-component gases with minimal variability in thermal properties, stable temperature environments with dry, non-condensing flows. They are not recommended for multi-phase flows or gas with liquid carryover, e.g. saturated or condensing streams. Applications with rapidly changing composition, such as biogas or mixed process off-gas, highly corrosive or particle-laden gases without protective coating or filters. Free liquids on the heated sensor will falsely spike flow readings or damage the probe. For saturated services, upstream filters, knockout drums, or condensate traps are essential. Sensor design and response characteristics. Two sensing principles are available. Constant power anemometer, CPA, heats the sensor at fixed power, measures temperature difference. Slow response time, 20 to 60 seconds, suitable for stable background flows, e.g. room air purges. Constant temperature anemometer, CTA, actively adjusts heater current to maintain a set delta T. Fast response time, 1 to 3 seconds, better for control or dynamic gas measurement. The sensor must be fully immersed in the flow stream away from wall effects or stagnant zones. In large ducts or stacks, insertion-style probes may require multi-point arrays to capture representative flow, especially where profiles are irregular. Installation guidelines. Insert the probe into the center of the pipe or duct, 60 millimeters or more into the flow, avoiding contact with the opposite wall. Maintain correct alignment to the flow axis, typically perpendicular to the flow direction. Avoid high vibration points or locations near pulsating gas sources. Probes must be removed prior to flushing, steam out, or air blowing to prevent sensor burnout. Retractable assemblies are recommended for on-stream removal and cleaning, especially in dusty environments or continuous operation. Calibration and gas-specific configuration. Each unit must be factory calibrated to the specific gas or mixture it will measure. Generic air calibration may yield large errors if the gas composition changes significantly. Conversion factors between gases are not reliable due to the nonlinear influence of thermal conductivity and specific heat on the heat transfer curve. Electronics integration and diagnostics. Transmitters typically provide 4 to 20 milliamps output linear to mass flow. Optional HART or Modbus communication. Built-in diagnostics for signal strength, sensor condition, and temperature drift. Ensure that electronics are isolated from direct heat sources or sun exposure, housed in explosion-proof or intrinsically safe enclosures where required, mounted remotely from the probe if installed in extreme temperature or inaccessible areas. Conclusion: thermal dispersion mass flow meters are the go-to solution for dry, low-pressure gas flow, where simplicity, cost-effectiveness, and direct mass measurement are priorities. Their success depends on clean service, stable gas composition, and correct probe placement. When matched properly to the application, they deliver consistent, maintenance-light performance, particularly in plant utilities, environmental monitoring, and air-based process control. Differential pressure flow meters for proven, versatile measurement across process conditions. Differential pressure DP flow meters offer a robust, well-understood method of flow measurement across a wide range of industrial applications, including liquids, gases, and steam. By measuring the pressure drop across a flow restriction, they provide an indirect but accurate estimate of volumetric or mass flow, provided all variables, density, pressure, and temperature, are properly accounted for. They remain a preferred choice in many industries due to their simplicity, durability, and scalability, especially in high-pressure systems, safety-critical applications, or where regulatory familiarity is important. Core components and measurement principle. DP flow meters consist of two main elements: a primary element, such as an orifice plate, venturi tube, or flow nozzle, that creates a controlled restriction; a secondary element, typically a differential pressure transmitter, that senses the pressure drop and outputs a signal proportional to flow rate. Because the pressure drop is proportional to the square of the flow rate, the system requires careful calibration and pressure density compensation if mass flow or high accuracy is required. Selection and sizing strategy. Proper sizing is essential for accurate and reliable operation. Key points include the maximum expected flow should fall between 80 to 100% of the transmitter's upper calibrated limit. The minimum flow should be above 55 to 67% of the full-scale flow rate, depending on required accuracy class. If a single transmitter cannot cover the full operating range while maintaining accuracy, use multiple transmitters with overlapping spans or select an alternate flow technology. The orifice bore should be calculated based on actual process data and then rounded to a standard size for ease of maintenance and spare parts management. Primary element options and use cases. Square edge orifice plates, common and cost-effective, suitable for clean single-phase fluids. Venturi tubes, lower permanent pressure loss, ideal for larger lines or erosive services. Flow nozzles, better suited to high-velocity, high-pressure services. Restriction orifice plates, not used for flow measurement, but to limit flow or reduce pressure. Installation requirements and best practices. Flow accuracy depends heavily on correct installation. Maintain adequate straight-run piping upstream and downstream to stabilize the velocity profile. Avoid disturbances such as elbows, valves, or reducers directly upstream of the measurement point. Position the meter in a fully filled, non-aerated pipe for liquids and in non-condensing, debris-free gas lines. For vertical piping, upward flow is preferred for liquids to ensure the line remains full. Impulse line design and configuration. Impulse lines connecting the transmitter to the process tappings must be short and of equal length to minimize lag and imbalance, sloped and self-draining for gas service or free of gas pockets for liquid service, equipped with block, vent, and drain valves for isolation, calibration, and maintenance. In viscous, dirty, or hazardous services, impulse lines may require heat tracing, purging, or diaphragm seals to maintain operability and prevent plugging or freezing. Trip function and redundant measurement. In systems requiring both control and safeguarding, DP flow elements may be shared between transmitters serving different functions, e.g., one for control, one for shutdown. In these cases, the tapping arrangement must ensure signal isolation and measurement integrity, typically via 4-tap designs or dual manifold setups. Maintenance and calibration. DP meters offer good long-term stability but require periodic inspection and cleaning of orifice plates or venturi tubes to prevent erosion or fouling. Verification of transmitter calibration, particularly if operating across a wide turndown or under temperature variation. Drain and vent line integrity checks to avoid signal distortion due to trapped air or fluid. Conclusion. Differential pressure flow meters remain a cost-effective, flexible, and proven solution when correctly engineered. Their performance is highly dependent on proper sizing, installation, and impulse line management. But when these are done well, DP flow meters deliver solid accuracy and reliability across a broad spectrum of process conditions. Turbine flow meters for high accuracy volumetric measurement in clean liquid and gas services. Turbine flow meters offer a precise and repeatable method for measuring volumetric flow of clean, low viscosity fluids, particularly where high accuracy, fast response, and pulse output are required. They operate by translating the velocity of flowing fluid into rotational speed of a bladed rotor. The resulting signal is proportional to volumetric flow rate. This makes turbine meters especially well suited for custody transfer, fuel dispensing, blending, and utility monitoring, provided the fluid is free from contaminants and pressure remains stable. High accuracy, high repeatability, but service dependent. Turbine meters offer accuracy better than pi 0.5%, with some calibrated units reaching pi 0.15%. Excellent short-term repeatability, crucial for batching and proportional blending. Fast response time, ideal for dynamic flow conditions. However, their performance depends on stable fluid viscosity and temperature, clean, non-fouling fluids free from solids, wax, or entrained gas, stable upstream flow profile to ensure even rotor loading. Common applications: LPG, gasoline, jet fuel, diesel, and light oils; natural gas, nitrogen, and compressed air with proper bearing and material selection; hydraulic fluids, demineralized water, and solvents in industrial metering skids. Design considerations and performance limitations. Turbine meters require flow conditioning and straight runs upstream, downstream, typically 10 to 20 pipe diameters to ensure velocity symmetry. Viscosity changes affect rotor drag and linearity, requiring temperature compensation or recalibration when used outside of a narrow operating band. At very low or very high flow rates, rotor instability or cavitation may cause signal loss or damage. Mechanical and material requirements. Flanged connections are preferred for repeatable installation and maintenance. 316 stainless steel internals are standard, with tungsten carbide or ceramic bearings for high wear, non-lubricating services such as LPG or gasoline. In non-lubricating fluids, bearings must maintain a fluid film, achieved by using long axis or large diameter rotor designs to minimize wear and startup torque. Overspeed and pressure protection. Sudden flow surges, hydraulic shock, or valve slamming can overspeed the rotor and damage bearings or sensors. Flow limiting devices or control valves should be placed downstream to protect the meter. Filters or strainers are mandatory upstream to prevent debris from contacting the rotor. These must be sized for low pressure drop under clean and dirty conditions and protected by differential pressure indicators or alarms. Electrical and signal integration. Turbine meters provide pulse output, often with magnetic or optical pickups. Signal conditioners or amplifiers must be mounted close to the meter to preserve signal quality, especially in hazardous or noisy environments. Pulse signals can be scaled for totalizing, batching, or flow rate indication, and are easily integrated into PLCs or flow computers. Installation and support requirements. Install meters horizontally with the rotor axis aligned with flow direction. In liquid service, ensure meter is always full and air is vented during startup. In gas service, install upstream filters and automatic air eliminators to protect rotor stability. Provide mechanical support for heavy meters and ensure adjacent piping exerts no torque or misalignment on the meter body. Calibration and proving considerations. For custody transfer or fiscal applications, turbine meters require regular proving using master meters or compact provers. Meters should be calibrated on the actual fluid or with a known standard to maintain accuracy. For critical services, double pulse pickups or redundant signal paths can enhance reliability and detect anomalies. Conclusion: turbine flow meters remain a high-precision solution for clean, stable, volumetric flow measurement in both liquid and gas services. When properly applied with correct filtration, straight run lengths, and protective measures, they offer fast response, excellent repeatability, and compatibility with digital systems. Their value is best realized in custody transfer, blending, and metering skids, where consistent fluid properties and tight calibration control enable long-term, high-accuracy performance. Positive displacement meters for high-accuracy volumetric flow in custody transfer and viscous fluid applications. Positive displacement PD meters deliver direct, high-accuracy volumetric flow measurement by capturing discrete volumes of fluid between moving mechanical components. Each rotation or cycle of the internal mechanism corresponds to a known volume, making PD meters inherently linear, pulse-generating, and highly repeatable. They are the meter of choice in custody, transfer, loading terminals, blending skids, and high viscosity liquid applications, where precision is critical and flow conditions are well controlled. Unlike inferential meters, PD meters do not rely on velocity or pressure drop. They physically count volume, making them ideal for applications requiring totalization, batching, or fiscal accountability. Unmatched accuracy and repeatability built into the design. Typical accuracy, Schwarzmeyer 0.1% to Palesen 0.2%, even in fluctuating flow conditions. Maintains accuracy across broad viscosity ranges from light hydrocarbons to heavy fuel oils. Excellent turndown ratios, typically 10:1 or better, depending on fluid properties and meter design. PD meters are especially effective when fluids are clean, lubricating, and non-pulsating. Absolute volume measurement is required, independent of density or pressure. Local or remote totalizers or batch controllers are integrated for precise dispensing. Typical applications: custody transfer of LPG, gasoline, diesel, and lubricants. Truck or railcar loading systems with ticket printers or preset batch control. High viscosity products such as asphalt, syrup, and waxes. Additive injection systems where tight volume dosing is required. Mechanical design and service constraints. Meters use gears, pistons, vanes, or oval rotors to divide and measure volume. Require clean, non-particulate fluids. Solids can jam or damage internal components. Non-lubricating fluids, e.g. LPG, water, cause bearing wear unless specially designed. High viscosity can raise pressure drop, must be considered in cold start scenarios. Pressure drop through PD meters is generally higher than that of turbine or Coriolis meters, especially in high viscosity or cold fluids. Oversizing the line, preheating, or using pressure-reducing bypasses may be required in such cases. Installation requirements and mechanical protection. PD meters must be installed with flange connections, level and properly supported. Piping must exert no strain on the meter body. External forces can deform internal tolerances. Strainers or filters upstream are mandatory to protect precision internals. These must be sized for low pressure drop when clean, capable of withstanding high differential pressure when fouled, 3 bar, equipped with DP indicators or alarms for timely maintenance. Gas eliminators or air vapor separators must be included in liquid service to prevent air locking or volume error. Overspeed and shock protection. PD meters can be mechanically damaged by overspeed, especially during rapid startup or valve slam events. Flow control valves, soft start sequences, or flow limiters should be used upstream to mitigate this risk. For high-pressure applications or fast-acting valves, consider hydraulic dampening. Signal and output integration. Pulse output is standard, ideal for connection to totalizers, PLCs, or flow computers. Mechanical or magnetically coupled counters can be used in hazardous or isolated areas. Where multiple outputs are required, e.g. batching and recording, use dual pickup systems with independent signal conditioning. Maintenance and calibration considerations. PD meters require routine inspection and periodic recalibration, especially in fiscal service. Wear of internal moving parts can lead to drift over time, particularly in non-lubricating or abrasive services. Many units include mechanical calibration mechanisms or adjustable gears for field tuning. For critical accuracy, proving systems such as compact provers, master meters, or tank provers are used to verify meter performance. Proving may be continuous or periodic, depending on contract or regulatory requirements. Structural support and layout. Larger PD meters are heavy and bulky, requiring mechanical handling for installation and removal. Must be installed in locations with overhead access or lifting equipment. Ancillary devices like filters, strainers, air eliminators, and flow conditioning equipment must be mounted for safe, accessible maintenance. Conclusion. Positive displacement meters provide true volumetric flow measurement with unmatched accuracy in clean, steady liquid flows. When correctly applied with proper filtration, vapor handling, and mechanical support, they are exceptionally reliable in custody transfer, blending, and loading applications. Their mechanical nature demands attention to fluid quality and flow conditions, but in return, they deliver robust, high-integrity measurement trusted across the energy, chemical, and transport sectors.